morning, everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of EC IARE. Yeah, today we are talking about DSP with the properties of discrete Fourier transform. So here, in this case, uh, the properties, before entering this all properties, so we are to verify that the properties of DFT within this. So we know that DTS and CTS and so on, discrete time signal processing, discrete time signals, discrete time systems. With reference to that, we know that but here DFT, it is the efficient computing for this all properties, where it is the powerful tool with reference to Fourier transform versus discrete Fourier transform. We will verify after completion of this all properties. The properties of DFT, discrete Fourier transform, since here DFT pair is equal to DFS pair with 0 point, here it is 0.0 n minus 1, 0 n minus 1. So here it is, okay. Their properties will be identified if we take care of these values of the x of n and x of k. Where x of n is, we know that IDFT, inverse discrete Fourier transform, where x of k is the DFT, discrete Fourier transform. When the indices are outside the interval, we are right to recognize this DFT pair equal to DFS pair with the 0 and minus 1. So basically we are having that first property. Let where x1 of n and x1 of k, because of we know that x of n and x of k. With reference to this, let x1 of n and x2 of n, x2 of in terms of the x2 of n and x2 of n comma x2 of k be two DFT, discrete Fourier transform pair with the same duration of capital N. Where so we have that ax1 of n plus bx2 of n and ax1 of k plus bx2 of k. So note that if x1 of n and x2 of n are of different lengths, we can properly appended zeros to the shorter sequence to make them with the same duration. Okay, with this the properties, the DFT, discrete Fourier transform, and inverse discrete Fourier transform for an n-point sequence x of n are given as discrete Fourier transform. So under discrete Fourier transform, it is followed by x of k is equal to the summation n is equal to 0 to n minus 1. Here n is equal to 0 to n minus 1, n is equal to 0 to n minus 1 x of n. That weight is twiddle factor x of w of n kn, where the k value is substituted, k equal to 0, 1, 2, 3, 4 and so on up to n minus 1. Yeah, coming to this inverse discrete Fourier transform, where x of n is equal to 1 by n, the summation, k equal to 0 to n minus 1, x of k with the into that twiddle factor wn power minus kn. Here we have to substitute that n value is n is equal to 0, 1, 2, 3, 4 up to n minus 1. So where wn is defined as wn is equal to e power minus j 2 pi by capital N. So in this content, we discuss about the important properties of the DFT. These properties are helpful in the applications of discrete Fourier transform to practical problems. Like in real-time problems, we will solve by using the major properties and the DFT, discrete Fourier transform. The notation used below to denote that n-point DFT pair x of n and x of k is where x of n DFT and n x of k. Like this, we will ready to represent the notation. The notation is based on this n-point discrete Fourier transform pair x of n and x of k. Okay, the coming to this linear property. Yeah, if DFT x1 of n is equal to what do you call x1 of k, and discrete Fourier transform x2 of n is equal to x2 of k, then DFT discrete Fourier transform a x1 of n plus b x2 of n is equal to a into x1 of k plus b into x2 of k. Okay, with this, the periodicity, yeah, the linear property, if it is x1 of n and with the DFT n and x1 of k, we'll write to verify. x2 of n DFT with n and n is increases, n is varies, x2 of k, it is measured a definition or statement of linearity under properties of discrete Fourier transform. Yeah, coming to the next periodicity. So if x of n and x of k are n point DFT pair, then x of n plus n is equal to x of what do you call x of n for all n. X of k plus n is equal to x of k for all capital N. Okay, like this, right, to verify that what you call periodicity. So now under in depth of this all periodicity. So if x of n and x of k are an n point discrete Fourier transform pair, then we are to verify these two conditions. So normally the periodicity, if x of n and x of k are an n point discrete Fourier transform pair, then x of n plus small n plus capital N is equal to x of n for all n, and x of k plus n is equal to x of k for all k. Like this, so easily can represent that all periodicity in terms of the discrete Fourier transform as well as inverse discrete Fourier transform. So this particular property, periodicity, right, to analyze that all what you call fiddle factor or weighting function. With this, the periodicity property with the weighting function Wn power k plus n is equal to Wnk, where we know that Wn is equal to e power minus j 2 pi by capital N. Where Wn k plus n is equal to e power minus j 2 pi by capital N into k plus n. So go on using this all steps, right, to simplify this Wn k plus n is equal to e power minus j 2 pi by capital N into k plus n. So why don't you simplify this one is where it is equal to e power minus j 2 pi by capital N into k into e power minus j 2 pi. Like this value is what you call in terms of the 1, where it is all coming from this e power minus j 2 pi is equal to cos 2 pi minus j sin 2 pi is equal to 1. According to this, should be 1, where Wn k plus n is equal to e power minus j 2 pi by capital N into k into 1. So finally that the weighting function or twiddle factor Wn k plus n is equal to e power minus j 2 pi by capital N into k. So here it is, the k is common to this e power j 2 pi by n. So where it is Wn k plus n is equal to Wnk. So like this, we are to verify that periodicity, importance of the periodicity, how it is analyzed in mathematically, how it is reflected with the twiddle factor and weighting functions. For efficient computation purpose, we will analyze this type of property, that is going to be a periodicity. Next property is time reversal. So if discrete Fourier transform x of n is equal to x of k, then DFT, the discrete Fourier transform of x of n minus capital N minus small n is equal to x of n minus k. So next property here, it is the shifting. So if discrete Fourier transform x of n is equal to x of k, so then discrete Fourier transform of x of n minus n naught is equal to x of k into e power minus j 2 pi kn naught by capital N. Okay. Now the circular shift, we have to verify that the linear shift when sequence is shifted, how it is shifted is you can analyze. So now symmetry property. So for a real sequence, if x of n to x of k, x of n minus k is equal to x convolved with k for the complex sequence, the discrete Fourier transform of x convolved of n is equal to x convolved of n minus k. So how it is represented if x of n, x of k. So if if x of this particular value, f x of n is nothing but real and even, right, to verify. But this case x of k. Okay, here it is inverse discrete Fourier transform, representation of inverse discrete Fourier transform. Here it is DFT. Then here it is real and even. But here x of k, real and even. But if you are using the x of k, real and odd, but this case is imaginary and odd. Easily you can distinguish this x of n, x of k. But in under x of k, odd and imaginary. Coming to this x of k, real, odd. The last one is the x of n, even and imaginary, and coming to the x of k, imaginary and even. Like this is you can distinguish this according to our symmetry property. For real sequence, if x of n to x of k. Okay, but easily you can ready to analyze this for this particular property for the complex sequences. How we will estimate both discrete Fourier transform and inverse discrete Fourier transform. Okay, now divide and conquer. This is, you can consider the case capital N is equal to Lm, where n can be factorized into the product of two integers, where n is equal to 0 is substituted. You can assign that x of 0, where n is equal to 1, x of 1, n is equal to 2. Here is x of 2 and n is equal to 3, x of 3, and so on, where small n is equal to n minus 1, where x of capital N minus 1. Consider the mapping where small n is equal to L plus m into capital L. Here go on substituting this value that so 1 by m is always L by m 0 the time. So if it is this value is 0 and 1, 2, 3 and so on up to m minus 1, where this value is 0, x of 0, here is x of L and so on, x of m minus 1 into L. Like this, where this value is 2, x of 1, x of L plus 1, where this m minus 1 case, where x of m minus 1 into L plus 1. So and so on, where this value is 2, x of 2, x of L plus 2, and so on, x of m minus 1 into L plus 2. Like this up to go on increasing this 2, 3, 4 and so on. Finally L minus 1, where here under 0 x of L minus 1, where 1 x of 2 into L minus 1 and x of ml minus 1. Like this we can consider this is the divide and conquer. Values are assigned. Okay, so for n, high composite can be factorized into the product of small prime numbers. Say for example here it is where capital N is equal to R1 into R2 into R3 into R4 up to RV. We can decompose the discrete Fourier transform of large order of into a sequence of small DFT discrete Fourier transforms. Example where N is equal to 210, that means 2 into 3 into 5 into 7 and so on. Like this, an example of the flow of computations of the 15-point DFT decomposed into L is equal to 3, M is equal to 5. Here is where L is equal to 1, 1 and L is equal to 2, where L is equal to 3. That means where L is equal to 3. This is part 1 and part 2, part 3 where L is equal to up to here. L is equal to 1, L is equal to 3. Where M is equal to, where this case M 1, 2, 3, 4, 5. That means where M is equal to 5. The time. So here we are ready to consider this 3-point DFT, 5 of them. 1, 2, 3, 4, 5. 5 of them. So we are ready to verify that what you call 5 out of 5-point DFT. Output response is what you call X of 2, X of 0, X of 3, X of 6, X of 9 and X of what you call 12. Like this we are ready to verify that in terms of practical aspect. Or a real-time example, we require the divide and conquer concept where it is the flow of computations for 15-point DFT decomposed into where L is equal to 3 and M is equal to 5. Okay, like this, to avoiding the time domain aliasing. How to avoid that time domain aliasing? So here is recall our notation that Wm is equal to e power minus j 2 pi by capital M. We have seen that previously that M is assigned the DFT and so on. If M point DFT of the finite length sequence xi of n with length ni, based on that xi of k is equal to the summation n is equal to 0 to ni minus 1 into that xi of n into that twiddle factor Wm where that k is substituted here. The k is equal to 0, k equal to 1, k equal to 2, k equal to 3, k equal to 4 and so on, m minus 1. So must satisfy that m, that capital M versus ni. So these two values, capital M point DFT with length ni, that capital M greater than or equal to ni, to avoid time domain aliasing and computing inverse discrete Fourier transform M of DFT M xi of n. Like this, mathematically write to what you call writing that mathematical expression. Okay, like this, if x3 of n is equal to x1 of n convolved with x2 of n with x1 of n and x2 of n, both finite length sequences. If it is infinite, no, that we are unable to analyze this case, avoiding that time domain aliasing, where with x1 of n and x2 of n both the finite length sequences, then the longest sequence is x3 of n with the length is n is equal to n1 plus n2 minus 1. Okay, this simplifies that our discrete Fourier transforms x1 of k, x2 of k and x3 of k should all be of what you call length. We should follow this length capital M greater than or equal to n1 plus n2 minus 1. To avoid time domain aliasing, in other words, we have to use this mathematical expression. Easily we can avoid time domain aliasing. x3 of n is equal to inverse discrete Fourier transform M of discrete Fourier transform M x1 of n into DFT M of x2 by n. Okay, so with this will result in x3 of n is equal to x1 of n convolved with x2 of n if the condition, this condition we have to apply. if m greater than or equal to n1 plus n2 minus 1. Like this, using this all notation, mathematical expressions must and should satisfy that m greater than or equal to ni to avoid time domain aliasing when computing inverse discrete Fourier transform. Okay, like this we have to recalculate these all points. Of that we try to verify that final results will be in x3 of n is equal to x1 of n involved with x2 of n if capital M greater than or equal to n1 plus n2 minus 1. Okay, so like this we try to verify that one simple example. If you suppose x1, if it is x1 is given 1 comma 2 comma 3 and x2 is equal to 1 comma 1 comma 1, we can compute the linear convolution as here. If we instead compute x3 of n is equal to inverse discrete Fourier transform m of DFT m of x1 of n into DFT m x2 of n. We are ready to calculate that m x3 of n. Like here the 6 and like this, where it is how many elements? 3, m equal to 3. Here it is what you call 4, where m is equal to 4. Here it is 1, 2, 3, 4, 5. So where m is equal to 5. Here this 1, 2, 3, 4, 5, 6, where m equal to 6. Observe that this is the time domain aliasing of x3 of n is avoided for m, capital M greater than or equal to 5. Like this, we try to verify in what you call problem oriented. Okay, now if it is very much useful in real time problems for designing what you call I say what you call in terms of these digital filters, how it is reflected. That will somewhat it is involve this type of computing. Another example, the DFT of a rectangular pulse. So x of n is of length is 5. Say for example, so we can consider x of n of any length greater than 5. How it is reflect? How happened? How it is variation with this DFT of a rectangular pulse? So let's pick this where because of its length is given. Okay, that capital N is equal to 5. So calculate the DFS of the periodic form of x of n. For this case, so we know that approximately x of k is equal to n is equal to 0 to capital N minus 1. N is given where n is 5. 5 minus 1 is 4. Okay, that x of k, approximately x of k is equal to the summation n is equal to 0 to capital N minus 1. M is given that 5 minus 4 is what you call 5 minus 1 is equal to 4 into e power minus j 2 pi k by 5 into n. So we have to simplify this one, e power minus j. So 1 minus e power minus j 2 pi k by 1 minus e power minus j 2 pi k by 5. So after that we try to simplify this one, that x of k approximately 5 if k equal to 0 plus or minus 5 plus or minus 10 and so on, 0 else. Like this, try to verify that DFT of the rectangular pulse. The pulses are like this. This is a rectangular pulse is given 0 to 4, 0, 1, 2, 3, 4 up to how many? Okay, like this, where it is x of n. The approximation after calculating this, we try to verify this all are 10 here where 5 and k equal to 0, k equal to what is plus or minus 5 or 10 plus or minus 10 plus or minus 15 plus or minus 20 and so on. Okay, otherwise where approximately we try to verify that what you call x into e power j omega here and so on. This we can analyze then graphically. With reference to that, the DFT of a rectangular pulse x of n is of length 5. we have to consider x of n of any length greater than that 5. Okay, like this we have to analyze. If we consider x of n of length is 10, what happens? Here is length is 5 only. How it is reflected in graphical and mathematically? If we consider x of n of length is 10, okay, we get a different set of discrete Fourier transform coefficients. Okay, like still samples of the discrete Fourier transform, but in different places. How? So here, where x of n is 0, 1, 2, 3, 4. N versus that x of n, where n versus x approximately n, like this, ready to analyze in graphically, where k versus x of k versus x of k with this values, right, to analyze still the samples of the dt discrete Fourier transform, but in different places will be identified, where x of n versus x of n and n versus x of n, approximately x of n, and k versus what you call x of k, and k versus what you call approximately k x of k. Okay, like this, if you consider the x of n of the length of 10, we will observe we get the different set of DFT discrete Fourier coefficients, samples of the discrete time Fourier transform built in different places. Okay, next property is linearity. Already we have seen. So with reference to that linearity, here also somewhat it is connected to duality. Okay, so where x of x1, here the x1 of n, so with the DFT x1 of k, x2 of n, they apply the DFT x2 of k, and a x1 of n plus b x2 of n. After applying this DFT with a x1 of k plus b x2 of k, with this the duality x of n. Okay, so apply with the DFT discrete Fourier transform, we will expect that x of k. If you are applying the x of k with the DFT, we will ready to what you call expect that x of n. Okay, here DFT, here is IDFT, here is DFT. X of n is apply the DFT, we will expect that x of k. Apply here where inverse discrete Fourier transform. Similar case, x of n, so n into minus k n, like this, the duality is ready to verify mathematically. Okay, next one is circular shift of the sequence, where x of n, ready to apply this discrete Fourier transform, we will expect the x of k. Similar case, x of n minus m into n with 0 less than or equal to n less than or equal to n capital N minus 1, the DFT x of k e power minus j 2 pi k by capital N into n, like this. So graphically, right, to verify that. Okay, n versus x of n, 0 and n, and where n versus x approximately n, and n versus approximately x1 of n is equal to x of n plus 2, where x1 of n is equal to x1 approximately what you call x1 of n 0 less than or equal to n less than or equal to capital N minus 1. Okay, 0 otherwise. Yeah, next duality example, here we are right to verify this one, and problem particular we will verify that. Next property is symmetry property. This property, somewhat it is right to verify that how it is variation of the DFT IDFTs. Here x of n minus m into n, where here wn kn x of k, wn e power en x of n, x of k e l of n. The summation m is equal to 0 to n minus 1, x1 of m into x of n minus m into n. Like here, x1 of k, x2 of k. Like this, x1 of n and x2 of n. So if you want to multiply this all are 1 by n, the summation L is equal to 0 to n minus 1, or n is equal to 0 to n minus 1, x1 of L, x2 of k minus L into n. Like this, we are right to verify this all this particular symmetry properties. Next one, here there is a proof with the symmetrical property, symmetry property. The proof is similar to that periodicity, where Wn k plus n plus k plus n by 2 is equal to minus Wn power k. We know that where the twiddle factor is equal to e power minus j 2 pi by capital N. According to this, Wn k plus n by 2 is equal to e power minus j 2 pi by capital N of into x plus n by 2, k plus n by 2. So go on simplifying this one, same notation for this, since we know that e power minus j is equal to cos pi minus j sin pi is equal to minus 1. Like this is 1, it becomes 1. That means Wn k plus n by 2 is equal to e power minus j 2 pi by capital N into k into 1. So finally that twiddle factor is equal to e power minus j 2 pi by capital N into k into minus 1. Okay. So here it is, you have to simplify this one, e power minus j 2 pi by capital N into power k is equal to polarity, based on this polarity minus W n k. Symmetry property, the polarities are changed. Periodicity property, the polarities are reversed. There is a major difference between that property and this property. We have to analyze in efficient computation the DFT discrete Fourier transform. We have to analyze. We have to remember these all properties. After that, we have to calculate that all, how it is reflected DFTs. Okay. Next, symmetry property. Here, by using this solver, after that Wn n by Wn square is equal to Wn by 2 more, and Wn is equal to e power minus j 2 pi by n, where it is here Wn by 2 is equal to e power minus j 2 pi by capital N by 2. After simplifying this, Wn square, but previously it is not that polarities are somewhat it is changed. Wn square is equal to Wn by 2. So direct computation of the discrete Fourier transform does not exploit this symmetry and periodicity property. So that is the greatness, that is the importance of this symmetry and periodicity properties. Using this all property of that, we like to verify that there is efficient computations of the discrete Fourier transform or IDFT or U for we will implement based on this, that with this DFT with the fast Fourier transform algorithm. Okay. Now here this is all we know. Yeah. Next, linear convolution. With this linear convolution using what do you call DFT. This is somewhat here it is x3 of n is equal to summation m is equal to minus infinity to plus infinity x1 of n m into x2 of n minus m. So recall that linear convolution is in mathematically where when the length of x1 of n and length of x2 of n are L and P. The length of x3 of n is L plus P minus 1. Now we know that convolution, linear convolution, circular convolution using direct method or by using the mathematical multiplication method. Here also we have to recollect after that. So thus a useful property is that circular convolution of two finite length sequences. Okay, the circular convolution of two finite length sequence with the lengths being L and P respectively is equal to the linear convolution of the two endpoint sequences obtained by zero padding. So that means that n, capital N greater than or equal to L plus P minus 1. So this is the important property while you are computing discrete Fourier transform with a linear convolution, how it is efficient. A useful property is that the circular convolution of the two finite length sequences with the lengths being L and P is equal to linear convolution of the two endpoint sequences obtained by zero padding. Okay, like another useful property is that we can perform circular convolution and see how many points remain the same as those of linear convolution. So by using this all interpretation, we can analyze the linear convolution and circular convolution, how it is important, how they are calculating, what the importance of this particular property while computing efficient computation level with the discrete Fourier transform DFTs. Okay, when P less than L and L point circular convolution is performed, the first P minus 1 points are what you call corrupted by circulation. Okay, and then remaining points from the n is equal to P minus 1 to n is equal to n minus 1, where n is equal to capital L minus 1. Like this, we will interpret this all in linear convolution with the circular convolution with the P less than L and then L point circular convolution is performed. Okay. Next, the last L minus P plus 1 points are not corrupted. So practically or manual operation, directly we have to observe this one, that the particular values are L minus P plus 1 points are not corrupted. If it is corrupted, try to verify that overlap save, that we are to analyze this particular property based linear convolution with the discrete Fourier transform. Okay, so that is the last L minus P plus 1 points remain the same as the linear convolution results. Using the different best example is we will analyze this particular points. We have lot of problems with this DFT, discrete Fourier transform, with IDFT, discrete Fourier transform, that we will analyze these 2 points. So that means the L minus P plus 1 points are not corrupted. L minus P plus 1 points remain the same as the linear convolution results. We will justify using the different what you call examples or problems. Okay, and linear circular convolution with the necessary, you have to collect this one linear convolution property. Okay, like this, x3 of n is equal to x1 of n, come out with x2 of n. Apply this, x3 of e power j omega is equal to x1 of e power j omega into x2 into e power j omega log omega then r. If the necessary discrete time Fourier transform exists, if x1 of n is length is n1 and x2 of n is length is n2, then x3 of n will be length we will expect that all capital N3 is equal to n1 plus n2 minus 1. Like this, we will analyze that linear and circular convolution. Okay, with the linear circular properties. For DFT, we have the circular convolution property. The circular convolution property with this, x3 of n is equal to x1 of n converted with x2 of n, and x3 of k is equal to x1 of k into x2 of k. This k equal to 0, 1, 2, 3 up to n minus 1. Okay, with this x1 of n converted with x2 of n is equal to the summation. So here it is circular convolution. Okay, n1 of n circular convolution, x2 of n is equal to what you call the summation k equal to 0 to n minus 1 x1 of k into x2 of n minus 1 into n. It is also equal to the summation k equal to 0 to n1 of n minus k into n x2 of k, where x1 of n and x2 of n must have the same length. Capital N is equal to n1 is equal to n2, and then the result x3 of n will also be length capital N. Okay, the linear convolution with the DFT, discrete Fourier transform. Suppose we want to compute x3 of n is equal to x1 of n convolution into x2 of n. You would compute the discrete Fourier transform of x1 of n and x2 of n, take their product, and then compute the inverse discrete Fourier transform to get x3 of n. So that is nothing but x3 of n is equal to inverse discrete time Fourier transform of discrete time Fourier transform of the x1 of n into discrete time Fourier transform of x2 of n. Okay, that means the compute the DFT of the x1 of n and x2 of n. How they will computing this all using this linear convolution with this discrete time Fourier transform. So we have to follow this all step-by-step procedure. That we like to verify that the compute the inverse discrete Fourier transform, we will get that all x3 of n. Okay, so what if we want to use this discrete Fourier transform to compute the linear convolution? Linear convolution, instead we know x3 of n is equal to inverse discrete Fourier transform of discrete Fourier transform of x1 of n into discrete Fourier transform of x2 of n. Compare this value and this value. Okay, how DFT, how they are computing the DFT. We have to follow this DFT to compute the linear convolution. Okay, so where x3 of n is equal to inverse discrete Fourier transform of discrete Fourier transform of x1 of n into discrete Fourier transform of x2 of n. Will not work because this performs circular convolution. Okay, here the circular convolution, right? Here it is not, will not work with because this performs the circular convolution. So as per your notation, if we want to use this DFT to compute the linear convolution, instead we know that x3 of n will not work with because this performs circular convolution. Now we have to enter that. So we have that circular convolution. The circular convolution of the two finite length sequences. So like x3 of n is equal to the summation m is equal to 0 to n minus 1 x1 of n into x2 of n minus m n with this x3 of n summation m is equal to 0 to n minus 1 x2 of n into x1 of n minus m n. Okay, like this x2 m versus x2 of m, like this. How many length? The sequences are 0, 1, 2, 3, 4, and then to here m versus x1 of m, like this. If x2 of 0 minus m and 0 less than or equal to m less than or equal to n minus 1, like this, right? To verify that circular convolution. Before that circular convolution, how it is happened with m versus m2 of n. Okay, circular convolution 2 rectangular. So rectangular pulses L is equal to n is equal to 6. Okay, so how they are verifying the DFT of the each sequence? We will verify by using the circular convolution of 2 rectangular pulses. Okay, of that how it is multiplication of the DFTs, discrete Fourier transform. Okay, so in the mathematical notation for this, in the circular convolution of the 2 rectangular pulses, where L is equal to n is equal to what you call 6. That means L is n equal to n is 6. For this, finally, and the inverse, so DFT, discrete Fourier transform, we will calculate, we will observe. So for this case, the pulses L is equal to n is equal to 6, x1 of n is equal to, x2 of n is equal to 1, 0 less than or equal to n less than L minus 1, 0 else. So like this, the DFT of each sequence, x1 of k is equal to x2 of k is equal to the summation n is equal to 0 to n minus 1 e power minus j 2 pi by capital N into k into n. If it is, that is also equal to n, k equal to 0, 0 else. Like this, DFT, discrete Fourier transform of each sequence, we will evaluate, we will compute. So next, multiplication of the DFT, discrete Fourier transform, x3, that x3 of k is equal to x1 of k and x2 of k is equal to n square, where k equal to 0, 0 else. Next step is will be appeared where in x3 of n, where x3 of n is equal to n. Okay, so then the DFT less than or equal to n less than or equal to n minus 1, 0 else. This is the mathematical notation. For this, we will expect in practically with the help of that mathematical tool, that MATLAB. Try to verify this, writing the piece of code. After that, we will try to verify n versus x1 of n, where n versus x2 of n, and so with reference to this, for the circular convolution, we will expect n versus capital N. x3 of n is equal to x1 of n, circular convolve with x2 of n. So this is possible for a manual as well as what you call that practically. Next example, we can augment zeros to each sequence where L is equal to 2, N is equal to 12. Say for example, the DFT of each sequence, so how it is varies, how they are multiplying of the DFTs, discrete Fourier transform. With this, the DFT of this sequence, x1 of k is equal to, x2 of k is equal to 1 minus e power minus j 2 pi L into k by capital N, because of L is given, okay, the 2 in place of here, by 1 minus e power minus j 2 pi, okay, into k by n. After that, we try to verify that the multiplication of the discrete Fourier transforms, x3 of k is equal to 1 minus e power minus j 2 pi L into k by n by 1 minus e power j 2 pi into k by capital N, where capital N is, you know that capital N value, after substituting this capital N, you should try to analyze, you try to multiply this one, go on using this k equal to 0, what happens if k equal to 1, k equal to 2, 3 and so on. We will evaluate, we will compute this augment zeros to each sequence, L equal to 2 and N is 12. We try to verify that the DFT of each sequence as well as multiplication of discrete Fourier transforms. So graphically, we try to verify n versus x1 of n like this. See how many samples are easily analyzed. 1, 2, 3, 4, 5, 6 and L and up to n versus x1 of n. Similarly, that n versus x2 of n, like this, how it is shifted, either right shift or left shift, or easily can analyze. Next one is x2 of n or n, that's 0 less than or equal to n less than to n minus 1. Here also n minus that x2 of this particular value. After that, so n versus this value where 0 less than or equal to n less than or equal to n minus 1. Practically it is available. Manually we will try to evaluate, we will compute we can augment 0 to each sequence where L is 2 and N is 12. How they are computing, how they are DFT of the each sequence, after that conclusion of discrete Fourier transform. Okay, like this, finally the circular convolution will be appear like this: N versus x3 of N is equal to x1 of N circular convolution x2 of N. Okay, where where DFT analysis equation, we will see that where x equal to Wx in terms of the weighting function, where inverse DFT synthesis equation, it is followed by x is equal to 1 by n w, and it was convolved with the x. Okay, so let's recap our notations that involved with the DFT analysis equation or the inverse DFT synthesis equations, how it is variation. Here, if you are using, so where x of n, where t is real, if you are using that, where normally the x of t is, we can consider the CTS, continuous time signal, isn't it? We know that where x of t is a continuous time signal, with reference to that, where x is continuous with reference to time domain and real function. Similarly, where x of k is the integer, where in terms of x, if we will expect that where discrete time, maybe it is the time domain and real function. Similar case, where x of z, where z is the complex, where x is the z transform or z domain, or we can consider the complex function. Here is all our real function. Now once we are using this one, z transform, z domain with complex function. Next, coming to the x of f, this x of f is the real time where x discrete time Fourier transform, how they are varying this. Up to this level, there is a time domain. These two are time domain, right? To verify that a frequency domain with the complex function. Similar case, coming to our case, the DFT discrete Fourier transform, x of I is integer, where x discrete time Fourier transform, we have to analyze from this is the frequency domain with the complex function. Like this, the analysis equation, it is maybe what you call DFT or inverse discrete Fourier transform. Okay, so we will consider a simple example for this. So within this, where x is given, x equal to 3 minus 1 0 2, based on this all weighting functions, that weighting function minus j 0, here all are minus j 0, here it is minus j 0 1 2 3. Okay, next minus j 0 2 4 6, next 0 3 6 9, like this we have to represent, where x equal to wx equal to 4 3 plus j3 and 2 and 3 minus j3, because is a n by n matrix multiplication. So directly write to verify the order of the discrete Fourier transform is equal to n square. Faster DFT computation. How we are agreeing this faster DFT computation? There is a possibility by using this all known or unknown properties with proof easy to analyze. We will ready to compute faster discrete Fourier transforms. Okay, so take the advantage of the symmetry and the periodicity of the complex exponential properties. Using this particular two properties, symmetry and periodicity properties of the complex exponential, like the twiddle factor or weighting function, it is followed by Wn is equal to e power minus j 2 pi by capital N. So based on this, we have to verify that symmetric and the periodicity. Okay. For this, where symmetry property, where that weighting function twiddle factor Wn k n minus n is equal to Wn minus kn is equal to Wn kn into convert, where Wn kn is equal to Wn k of n small n plus capital N is equal to, if you are using this particular property. Using this major two properties, right, evaluate the faster discrete Fourier transform computation is possible. Remaining all are that fastest DFT discrete Fourier transform computation is not possible. Sometimes it is possible, but it is somewhat it is complexity. Okay. With this, note that two lengths length n by 2 DFT takes less computation than one length n DFT into 2 n by n square less than n2. Algorithms that export, if you are using this somewhat, you are right to observe that less computation, more computation, highest computations. So we are facing a lot of demerits while you are using faster DFT computation with that symmetry and periodicity. We will ready to verify that all. Further reducing the complexity, go for that different algorithms that exploit computational savings are collectively called FFT, fast Fourier transform. So we want to compute this, say the DFT or IDFT, maybe in FFT and so on. So you can consider export that computational saving are collectively called so that FFT. So we are analyzing this FFT, DFT, IDFT, and FFT, whatever it is, we require this type of important properties. Based on this property, we try to compute efficient computation while using this from the beginning for these jet transform on DFT, IDFT, and up to FFTs. So that is the importance of your properties related to the what you call involved with the DFT as well as FFTs. Okay.
Like, share and subscribe. Hit the bell icon for more updates.